A hidden architecture connects every galaxy in the cosmos. This is the cosmic web, the largest structure in existence, and understanding it will change how you see the universe forever. For centuries, we pictured galaxies as lonely islands adrift in a dark ocean. The truth is far more incredible. They are all interconnected points in a single, vast network that spans the entire observable universe. By the end of this journey, you will know the secret composition of this cosmic skeleton and how it dictates the ultimate fate of all things. What unseen force built this universal framework, and what does it mean that we are woven into its very fabric? How does it feel to know you are part of something this immense? William Herschel peered through his telescope and saw what he called island universes, scattered like lonely ships on a dark sea. This poetic idea held for over a century, a comforting picture of celestial solitude. But the universe had a different story to tell. The first crack in this worldview appeared in a single room in Washington, D.C., in the year 1920. There, two brilliant astronomers, Harlow Shapley and Heber Curtis, engaged in what became known as the Great Debate. They argued fiercely over the very scale of existence. Were these spiral nebulae simply part of our own Milky Way, or were they entire galaxies, unimaginably far away, each a universe of its own? The debate ended without a clear winner, but it set the stage for a revelation. Just a few years later, Edwin Hubble, using the most powerful telescope of his time, made an astonishing discovery. He found that these distant galaxies were all racing away from us and from each other. The universe was not static. It was expanding, stretching the fabric of space itself. This was the first crucial clue. If everything was moving apart in a specific, organized way, then the distribution of matter could not be random. There had to be an underlying architecture, a blueprint from the dawn of time guiding this great exodus. For decades, this architecture was just a ghost in the equations, a prediction of Einstein's theory of relativity and other cosmological models. Long before we could see it, mathematicians and physicists calculated that the newborn universe must have had tiny fluctuations, wrinkles in space that gravity would amplify over billions of years. These wrinkles would become the seeds for everything we see today, the invisible threads of the cosmic web. Our understanding had evolved from seeing isolated islands to sensing the presence of a vast, hidden continent. The question was no longer if it existed, but what exactly was this continent built from? The true nature of this cosmic architecture remained a ghost in the machine for decades, a mathematical necessity waiting for a physical form. That form is dark matter, the invisible skeleton of the cosmos. Think of the grandest bridge you have ever seen. You admire its sweeping cables and massive roadways, all made of steel and concrete. But what you cannot see are the deep foundations and the internal supports, the hidden framework that holds everything up and gives it shape. Dark matter is that framework for the entire universe. It is a substance that does not emit, absorb, or reflect any light, making it completely invisible to our telescopes. Yet its gravitational pull is the single most powerful force sculpting the cosmos. Right after the Big Bang, when the universe was a searing, dense soup of particles, tiny quantum ripples were frozen into the expanding fabric of space. Dark matter, responding only to gravity, began to cluster around these ripples. It collapsed under its own weight, first into tiny specks, then into vast, invisible clouds called halos. These halos became the gravitational wells, the cosmic pits that would trap everything else. Ordinary matter, the gas and dust that would eventually form stars, planets, and us, was simply along for the ride. Drawn in by the immense gravitational pull of the unseen dark matter, this normal stuff settled into the halos, cooling and condensing to birth the first galaxies. Without this dark scaffolding, the gravitational pull would have been far too weak to gather matter together. The universe would have remained a featureless, expanding fog, a silent and empty void with no galaxies, no stars, and no life. Every brilliant structure we see is just the visible decoration draped over an invisible frame. So when we map the glittering galaxies in the sky, we are not actually looking at the main structure. We are merely tracing the lights on the shore while the true continent lies hidden in the darkness beneath, and this raises a profound question. What else is woven into this invisible fabric that we have yet to discover? But if dark matter is the unseen skeleton, then what is the flesh and blood of the cosmos? This is the role of ordinary baryonic matter, the very stuff of stars, planets, and life itself, composed of the familiar protons, neutrons, and electrons. This is the luminous thread that weaves through the invisible dark matter framework, making the cosmic web visible to our eyes. Picture a vast, sprawling network of rivers and streams. The dark matter forms the deep, unseen riverbeds and the shape of the entire watershed. The ordinary matter is the water itself, flowing relentlessly along these predetermined channels. As this river of gas and dust is funneled along the dark matter filaments, it begins to cool and collapse under its own gravity. In the densest knots where these invisible rivers intersect, the pressure and temperature become so immense that nuclear fusion ignites and a galaxy is born. These brilliant galaxies are not randomly scattered. They mark the busy intersections of the cosmic web, the glittering cities along its hidden highways. For a long time, however, our cosmic inventory did not add up. We could count the stars and galaxies, but a huge amount of this normal matter was simply missing. The answer to this mystery lies in the vast, empty spaces between the galaxies. There, a diffuse, superheated gas known as the warm-hot intergalactic medium, or the WHIM, fills the voids. This is not a cold, empty vacuum, but a seething ocean of matter so hot it glows only in X-rays, invisible to optical telescopes. This WHIM represents the final piece of the puzzle, the long-lost reservoir of normal matter that had been hiding in plain sight. Our most powerful telescopes now paint this breathtaking picture, revealing the cosmic web not as a theoretical idea, but as a physical structure. They show clusters of galaxies connected by faint, glowing bridges of gas, tracing the very filaments predicted by theory. This stunning tapestry, woven from the interplay of the invisible and the visible, raises a monumental challenge. How do you begin to chart a continent you cannot see, using only the lights of the cities strung along its coast? The blueprint for this entire cosmic structure was drawn not by a telescope, but by mathematics. Decades before we had the tools to see it, the cosmic web existed as lines of code and equations, a ghostly prediction of our most powerful theories. The leading model of cosmic evolution, known as the lambda cold dark matter model, provided the essential recipe. It began with a universe that was almost but not perfectly smooth. The infant cosmos was imprinted with faint quantum ripples, tiny variations in density frozen into existence during a period of hyper-expansion called inflation. These ripples were the universe's original seeds. Over the next 13.8 billion years, gravity got to work. It treated these dense spots like magnets, relentlessly pulling dark matter toward them. Billions of years of this gravitational collapse sculpted the dark matter first into a vast, frothy network of filaments and halos, a cosmic skeleton. Ordinary matter then flowed into this pre-existing framework, lighting up the intersections with galaxies. This entire process was not just theorized, it was simulated. Visionary scientists like Jim Peebles used the most advanced supercomputers of their day to run the clock of cosmic evolution forward. They watched as virtual universes, born from random quantum seeds, grew into stunningly detailed webs that mirrored the large-scale structure we actually observe. These digital universes were the treasure maps. They told astronomers exactly where and how to look for the real cosmic web, transforming a theoretical phantom into a tangible, observable structure waiting to be found. How do you hunt for the largest thing in the universe when your maps are made of pure mathematics? Mapping the invisible requires a cosmic detective's toolkit, methods that see not with light, but with shadow and distortion. One of the most powerful techniques uses the universe's own lighthouses, quasars. These are the intensely brilliant cores of distant galaxies, powered by supermassive black holes, and they shine with enough power to be seen across the cosmos. As the light from a single quasar journeys for billions of years to reach our telescopes, it passes through the faint, diffuse gas of the cosmic web's filaments. Specific elements within this gas, like hydrogen and helium, act like cosmic filters, absorbing very particular colors from the quasar's brilliant white light. The result is a spectrum, a rainbow of light crossed by dark, missing lines, a unique barcode of absorption. Each line is a ghostly fingerprint, a record of an invisible filament the light passed through. But one quasar is just a single pinprick of insight, a narrow beam through the vast cosmic forest. To see the whole forest, you need more flashlights. Astronomers have turned this method into a grand statistical enterprise, analyzing the light from not one, but hundreds of thousands of quasars. By comparing these thousands of individual barcodes, they can perform a form of cosmic tomography, reconstructing the three-dimensional distribution and density of the hidden gaseous web. Another method abandons light altogether and instead watches for its bending. According to Einstein's theory, mass warps the fabric of space-time. The immense, though diffuse, mass of the cosmic web's dark matter and gas acts as a lens, subtly distorting the light from galaxies that lie far behind it. This effect, called weak gravitational lensing, causes the shapes of countless background galaxies to appear ever so slightly stretched and aligned, tracing out the gravitational field of the invisible web. It is like looking at a distant cityscape through the ripples of heat rising from a desert highway, the distortions revealing an unseen presence. These indirect probes are combined with direct, monumental efforts to chart the visible parts of the structure. Massive redshift surveys with names like the Sloan Digital Sky Survey have meticulously catalogued the positions and distances of millions of galaxies. This creates a three-dimensional pointillist map of the universe, where each galaxy is a single dot of paint. When you step back, the dots resolve into an immense, interconnected cosmic architecture, with vast voids bounded by great walls and filaments of galaxies. This multi-pronged assault, using shadows, distortions, and a celestial census, has finally given us our first true map of the cosmic continent. And at the very largest scales, this map reveals structures of such staggering size that they challenge our fundamental understanding of the cosmos itself. These glittering galactic cities are only half the story, for the cosmic web is defined as much by its emptiness as by its structure. Between the brilliant filaments and dense clusters lie the cosmic voids, incomprehensibly vast regions of near nothingness. A single void can stretch for hundreds of millions of light years, a volume of space so enormous it could contain thousands of galaxy clusters, yet it holds almost none. This is not a perfect vacuum, but a realm of profound solitude, home only to a few wandering, isolated galaxies and a whisper-thin haze of gas. These voids are the true counterweights to the dense nodes, the cosmic deserts that balance the glittering metropolises. Their existence is critical to the web's very dynamics. As the universe expands, these empty regions grow faster than the rest of the cosmos. Their boundaries push outward, and this expansion actually tugs on the surrounding filaments and clusters, influencing the motion of entire galaxies. It is a grand cosmic tug of war, a delicate dance between the inward pull of gravity within the dense web and the outward push of the expanding voids. This makes these empty spaces one of our most powerful laboratories for studying dark energy, the mysterious force accelerating the universe's expansion. By measuring how voids grow and change over time, cosmologists can test the strength of dark energy and understand the ultimate fate of all things. The sheer scale of these voids forces us to confront a humbling reality. For every brilliant island of stars, there is an ocean of profound emptiness 1,000 times larger. Our own Milky Way does not reside in a void, but within a bustling filament, a fortunate location that may have been essential for our own existence. What does it mean that the universe is primarily composed of these vast, silent, and ever-growing spheres of nothing? These vast voids are bordered by their polar opposites, the dense and brilliant backbones of the cosmos. At the intersections of the cosmic web's filaments, gravity has woven the universe's most colossal structures, the Great Walls and Superclusters. One of the largest ever mapped is the Sloan Great Wall, a staggering conglomeration of thousands of galaxies stretched across nearly 1.4 billion light-years. To grasp that scale, a beam of light, the fastest thing in the universe, would need 1.4 billion years just to travel from one end of this structure to the other. This is not a solid wall, of course, but a gauzy, interconnected plane of galaxies, a celestial continent floating in the darkness. The filaments that feed into these intersections are the true cosmic rivers. They are colossal streams of dark matter and hydrogen gas, flowing relentlessly toward the gravitational wells of the clusters. This constant influx of fresh, cold gas is the lifeblood for new star formation, fueling the birth of billions of stars within the resident galaxies. The environment within these dense backbones is anything but tranquil. It is a gravitational metropolis, a dynamic and often violent realm. Galaxies are pulled along these filaments like cars on a cosmic highway, frequently drawing too close to one another. When they do, their mutual gravity can warp their beautiful spiral shapes, strip away their gas, or trigger a cataclysmic merger, creating new, larger elliptical galaxies. This frenetic activity makes these regions the engines of galactic evolution, where the fate of entire galaxies is decided by their position in the network. And at the very heart of these superclusters, at the busiest intersections of the cosmic web, lie the most extreme and active nodes, where the universe's most powerful forces are on full display. At the very heart of the cosmic web's busiest intersections, gravity builds its ultimate metropolises. Galaxy clusters are the crowded downtowns of the universe, where thousands of galaxies are packed into a relatively small volume of space, all bound together in a ferocious gravitational dance. The space between these galaxies is not empty. It is filled with a searing ocean of plasma known as the intracluster medium, a gas so incredibly hot it glows not in visible light but in powerful X-rays. This thin, superheated fog is a substance of profound importance, for it contains more normal matter, more atoms, than all the stars in all the galaxies of the cluster combined. It is the true, dominant atmosphere of this celestial city. Within this dense and violent environment, galaxies live tumultuous lives. They do not drift peacefully. They whip past one another at incredible speeds, their mutual gravity pulling and twisting their spiral arms, stripping away their vital star-forming gas. Sometimes, a larger galaxy will gravitationally cannibalize a smaller neighbor, tearing it apart and absorbing its stars. In even more extreme encounters, entire galaxies can be hurled out of the cluster entirely, banished into the dark loneliness of intercluster space. These dynamic processes are a masterclass in the unyielding power of gravity, sculpting the shapes and destinies of galaxies. By studying these chaotic hubs, astronomers gain critical insights. The very existence and stability of a cluster depend on the immense gravitational anchor of dark matter, whose invisible halo holds the entire Metropolis together. The properties of the hot intracluster gas reveal the history of violent mergers and the intense gravitational pressures that heat it. Each cluster is not an isolated island, but a single, glittering knot in the vast cosmic net, a node that connects to even grander structures, the superclusters that form the continents of the observable universe. These galactic metropolises are themselves organized into something even grander, the continents of the cosmic web. Superclusters are the largest known structures in the universe, immense assemblies of galaxy clusters that can stretch for hundreds of millions of light-years. Our own home, the Milky Way, is not adrift in some random neighborhood. We are part of the Laniakea supercluster, a name from Hawaiian meaning immense heaven. This is our gravitational continent, a vast collection of about 100,000 galaxies all moving together through the cosmos. But here is the crucial distinction. While a galaxy cluster is a tightly bound city held together by its own gravity, a supercluster is not. It is more like a sprawling, continental watershed. All the galaxies within Laniakea are flowing along invisible gravitational currents toward a single, immense gravitational center known as the Great Attractor, a mysterious region of space that pulls on us from the depths of the cosmic web. Yet this entire continental structure is not collapsing. It is still expanding, carried along by the overall flow of the universe's expansion. Mapping these titanic structures gives astronomers a unique view of the cosmic web's largest currents. By tracing the subtle motions of thousands of galaxies, we can see how matter flows from the empty voids into the great filaments and finally toward these dense supercluster nodes. This grand pattern is a direct echo of the universe's earliest moments. The specific arrangement of superclusters we see today, their sheer size and distribution, were imprinted by those faint quantum ripples from the dawn of time. Studying them is like reading a fossil record of the infant cosmos, revealing the initial conditions that set the entire cosmic web into motion. This hierarchical pattern, from single galaxies to clusters to these immense continents, shows a universe built on a principle of interconnected scales. How far does this ladder of cosmic structure truly go? Gravity is the patient weaver of this cosmic tapestry, a relentless sculptor working across billions of years. It began its work when the universe was a nearly smooth, expanding cloud of matter and energy. In that near-perfect uniformity, tiny, random clumps existed, regions ever so slightly denser than their surroundings. These minuscule wrinkles were the only tools gravity needed. Its pull, an attractive force that weakens with distance but never truly vanishes, gave it an unimaginable reach. Over cosmic timescales, this force acted with immense patience, pulling matter from the vast, underdense regions and depositing it into the slightly denser ones. This process, known as gravitational instability, is elegantly simple. A region with a little extra mass exerts a slightly stronger gravitational pull, attracting more matter from its surroundings. As it grows more massive, its pull strengthens, accelerating its own growth in a powerful feedback loop that transforms a whisper of density into a cosmic shout. What started as quantum ripples no larger than a subatomic particle were amplified into the vast, intersecting filaments and colossal voids we observe today. Without gravity's unceasing, attractive pull, there would be no cosmic architecture. The primordial soup would have simply continued expanding, thinning out into a cold, dark, and utterly featureless void. There would be no galaxies, no stars, no planets, and no us. Every structure we see is a monument to gravity's persistent creative power, yet this force did not act alone. It required a canvas, a set of initial conditions upon which to work its magic. The specific pattern of the web we see was not random, but was imprinted by the universe's very first moments. The ultimate origin of the cosmic web lies in the very first moments of existence, in a fleeting instant of unimaginable transformation. To understand how gravity built its vast architecture, we must journey back to a time before the first stars, before the first atoms, even before the universe was 1 second old. This was the epoch of cosmic inflation, a period when the cosmos expanded faster than the speed of light, swelling from a subatomic speck to a volume far larger than our entire observable universe in a fraction of a blink. During this violent growth spurt, the empty vacuum of space itself was seething with energy, and within it, quantum fluctuations were inevitable. According to quantum mechanics, empty space is never truly empty. It is a frothing sea of virtual particles, constantly flickering in and out of existence. These fleeting bubbles of energy and warps in spacetime were the crucial ingredients. As the universe inflated at a phenomenal rate, these subatomic wrinkles were stretched, magnified, and frozen into the very fabric of the cosmos. What began as a quantum whisper on the smallest possible scale became a macroscopic imprint on the entire universe. These minute variations in density, these slightly denser and slightly emptier patches, became the primordial seeds for everything to come. Once inflation ended, the universe settled into a more sedate expansion, but the blueprint was already drawn. Those seeds were now baked into the cosmos, a faint pattern of hills and valleys in the density of the newborn universe. Gravity, which had been waiting in the wings, now took center stage. It began to pull matter, both dark and normal, toward these denser hills. Over billions of years, this gentle tug amplified the initial pattern, sculpting the faint ripples into the great filaments, clusters, and voids we map today. The cosmic web is, in essence, a colossal fossil. It is a frozen snapshot of quantum mechanical processes that occurred during the universe's first trillionth of a second. This profound connection is staggering to contemplate. The distribution of galaxies across billions of light years can be traced back to random, unpredictable quantum events on a scale a billion times smaller than a proton. It means the largest structures in existence are fundamentally rooted in the smallest, governed by the same universal laws. This realization is a cornerstone of modern cosmology, a breathtaking hint that the rules governing the quantum realm and the cosmic scale are one and the same. For decades, astronomers faced a cosmic accounting error of staggering proportions. When they tallied up all the ordinary matter created by the Big Bang, the numbers simply did not add up. Roughly half of it was missing. This was the infamous missing Baryon problem, a puzzle that haunted cosmology. The early universe left a clear ledger, a fossil light called the cosmic microwave background, which recorded exactly how much normal matter protons and neutrons should exist. Yet when we counted all the stars, planets, and cold gas in galaxies, we could only account for about half of that expected amount. Where had the rest gone? The answer was hiding in the most obvious place of all, the vast, empty spaces of the cosmic web. The missing matter was not in the brilliant galaxies, but in the filaments connecting them. It exists as a superheated, incredibly diffuse fog known as the warm-hot intergalactic medium, the WHIM. This gas is so thin, with just a few atoms per cubic meter, and so hot, at millions of degrees, that it does not glow in visible light. It is a ghost in the machine, completely transparent to our optical telescopes. To find it, astronomers had to become cosmic detectives, looking not for the gas itself, but for the shadows it casts. They turned to the most brilliant lighthouses in the universe, quasars. As the intense ultraviolet and X-ray light from a distant quasar travels across the cosmos, it passes through these faint filaments. Atoms within the WHIM, like oxygen and hydrogen, absorb very specific energies from this light, leaving dark lines in the quasar's spectrum. Each line is a ghostly signature, a chemical fingerprint proving the presence of this elusive hot gas. By piecing together millions of these observations, scientists finally confirmed that the WHIM is real and that it contains almost all of the universe's missing normal matter. This discovery was a monumental triumph. It solved a decades-long mystery and completed our inventory of the cosmic building blocks. It confirmed that the cosmic web is not just a dark matter skeleton, but also the universe's primary reservoir for its ordinary atomic content. The grand architecture holds not only the galaxies, but also the very substance from which they were forged. This raises a thrilling new line of inquiry. If the web holds the answers to our past, what other secrets about the future of the cosmos are woven into its invisible threads? This ghostly plasma is the final resting place of the universe's missing atoms. The warm-hot intergalactic medium, or the WHIM, is a gas so incredibly hot and thin it defies our everyday experience. Its temperature soars between 100,000 and 10 million degrees, a searing heat generated by the cosmic violence of galaxy formation and the titanic shock waves from supernova explosions. Yet despite this immense energy, it is almost a perfect vacuum. A single cubic meter of this space might hold just a handful of atoms, a density far emptier than any vacuum we can create on Earth. This paradoxical combination of extreme heat and extreme emptiness is what rendered it invisible for so long. We cannot see it with traditional telescopes because it is too diffused to glow brightly in any single wavelength. So how do you find a ghost? You watch for the shadows it casts. Astronomers use distant quasars as brilliant backlights. As this pure, white light journeys for billions of years, it passes through the WHIM filaments. Specific elements within the hot gas, like highly ionized oxygen, act like a cosmic filter, absorbing very precise slivers of energy from the quasar's light. The result is a spectrum, a rainbow of light crossed by a unique pattern of dark, missing lines. Each pattern is a chemical fingerprint, a spectral barcode that proves the presence of this invisible material. In the deepest voids, where the gas is too faint to even cast a shadow, astronomers search for its faint, diffuse glow in X-rays, a whisper of light from the hottest parts of the cosmic web. This discovery completes our cosmic inventory, solving the long-standing mystery of the missing matter. But the WHIM is far more than a hidden reservoir. It is the cosmic web's lifeblood, a vast circulatory system. The same gravitational currents that shape the web continually funnel this tenuous gas along the filaments. Over immense timescales, some of this material can cool and condense, flowing into galaxies to serve as the raw fuel for new stars. This reveals a dynamic and cyclical cosmic ecosystem. The violent deaths of stars in supernova heat and enrich the gas, blowing it back out into the web, only for gravity to eventually gather it once more, seeding future generations of stellar birth. The cosmic web is not a static sculpture. It is a living, breathing structure, and the WHIM is the vital breath flowing through its invisible veins. This grand architecture has not always looked the way it does today. The cosmic web is a dynamic entity with a biography spanning billions of years, and its youth was a time of frantic construction. In the first few billion years after the Big Bang, the universe was a much smaller, denser, and more intimate place. The cosmic web was a tighter, more intricate tapestry, with filaments that were thicker and more richly packed with fresh, cool gas. Matter raced along these primordial highways at a breathtaking pace, funneling directly into the voracious gravitational wells of young protogalaxies. This was the universe's golden age of star formation, a period of intense, brilliant activity fueled by this rapid influx of raw material. But this frantic pace of construction could not last forever. A fundamental shift was occurring, driven by an enigmatic force. As the universe continued to expand, the influence of dark energy began to grow. Think of it like this. In the universe's youth, gravity was the dominant force on the largest scales, tirelessly pulling matter together to build the web. But as space itself stretched, the distances between the great cosmic structures increased. Dark energy, which acts as a kind of repulsive force inherent to space, began to overcome gravity's grip. This was a turning point in cosmic history. The expansion of the universe started to accelerate. The consequences for the cosmic web were profound. The rate at which new structures could form began to slow. The great voids, those vast deserts of nothingness, started to expand at a faster rate, pushing their boundaries outward and stretching the filaments that connected the galaxies. The web did not dissolve, but it became more starkly defined, more polarized. Matter became increasingly concentrated within the nodes and filaments, while the voids grew ever larger and emptier. We are not left to merely theorize about this ancient history. Our most powerful telescopes are time machines, the Hubble Space Telescope's deep field images, and now the stunning infrared views from the James Webb Space Telescope allow us to look back in time directly. They capture the light from galaxies as they were when the universe was only a fraction of its current age. By comparing these ancient galactic cities to the ones in our modern cosmic neighborhood, astronomers can trace the web's evolution in exquisite detail. They can see the tighter clustering of young galaxies, the more abundant gas in the filaments, and witness the gradual thinning and stretching of the entire structure over cosmic time. Understanding this deep history is more than an academic exercise. It is the key that unlocks the future. The same forces that have shaped the web's past will dictate its ultimate fate, a destiny that appears increasingly lonely and diffuse. About 5 billion years ago, a cosmic tipping point was crossed. The relentless pull of gravity, which had spent billions of years tirelessly building the cosmic web, was suddenly challenged by a new, dominant force. Dark energy, a mysterious form of energy inherent to the fabric of space itself, began to accelerate the expansion of the entire universe. This was the moment the universe's construction project began to slow, and its great unraveling started. Think of the cosmic web as a sheet of elastic fabric, with galaxies and clusters dotting its surface. For eons, gravity has been gathering this fabric into dense knots and taut threads. Now, dark energy is stretching the entire sheet from all directions at once, pulling it tauter and tauter. This creates a cosmic tug-of-war of unimaginable scale. On one side, gravity works locally, pulling galaxies together within clusters and along filaments, trying to maintain the web's intricate architecture. On the other side, dark energy acts globally, stretching the very space between these structures, diluting their connections and thinning out the cosmic rivers that feed them. The filaments of the web, those great cosmic highways, are not snapping. Instead, they are being drawn out, becoming longer, thinner, and more tenuous. The vast voids between them are growing at an ever-increasing rate, becoming ever more empty. Over trillions of years, this stretching will have profound consequences. Galaxies that are not already bound in tight, gravitational groups will find themselves isolated. The flow of fresh gas from the cosmic web into galaxies will gradually be choked off, starving them of the fuel needed to form new stars. The universe, once a bustling network of shining cities, will begin to quiet down and grow dark. This relentless acceleration leads cosmologists to some startling visions of the far future. One possibility is the Big Freeze, where the universe continues to expand and cool, with galaxy clusters becoming isolated islands in an ever-growing sea of nothingness. An even more extreme fate is the Big Rip, where the repulsive force of dark energy grows so powerful that it overcomes all other forces, not just expanding space but tearing apart galaxies, solar systems, and even atoms themselves in a final, catastrophic moment. Which of these destinies awaits our cosmos depends entirely on the precise and still unknown nature of dark energy. Unraveling this mystery is one of the greatest quests in modern science, for it asks the most fundamental question of all. How will the story of everything ultimately end? To understand this grand architecture, we must create universes of our own. Inside the world's most powerful supercomputers, cosmologists run breathtakingly complex simulations, digital laboratories where they can watch the cosmos evolve from a blur of initial conditions to the intricate web we see today. These are not simple animations, they are rigorous calculations that use billions of virtual particles to represent dark matter and ordinary gas. Each particle feels the gravitational pull of every other particle, while the gas particles also experience pressure, shock waves, and the complex physics of star formation. The goal is stunningly ambitious: to start with a nearly smooth, expanding universe, sprinkle in the primordial quantum ripples we detect in the cosmic microwave background, and then set the clock forward for 13.8 billion years. The most famous of these projects, with names like Illustris TNG and Eagle, do exactly this. They run for months on thousands of computer processors, calculating quintillions of interactions. And the result is nothing short of miraculous. When the simulation is complete, the scientists can fly through their virtual cosmos. They find a fully formed cosmic web, complete with vast, dark voids, delicate, intersecting filaments of dark matter, and at the nodes, dense clusters of virtual galaxies that possess realistic shapes, sizes, and even chemical compositions. The fidelity is so remarkable that when you place a map from the simulation next to a map from a real galaxy survey, the two are often indistinguishable. This successful reproduction is one of the strongest validations we have that our core theories about dark matter and gravity are on the right track. But these digital universes are far more than just validations. They are experimental playgrounds. Scientists can run the simulation again and again, each time tweaking a single variable, perhaps making dark matter slightly more interactive or altering the strength of dark energy. They can then see which version grows a cosmic web that most closely matches our real universe. This process allows them to test the fundamental properties of the cosmos itself, exploring scenarios we could never witness, like a universe where dark energy is twice as strong, or where the initial quantum ripples had a different character. These virtual worlds bridge the chasm between the elegant mathematics of theory and the messy, beautiful reality of observation, giving us a powerful tool to decipher the hidden laws that built everything. The entire cosmic web was once contained within a single, glowing point. That point expanded and cooled for 380,000 years until it reached a pivotal temperature, cool enough for electrons and protons to combine into the first atoms. In that moment, the universe became transparent, and a flash of light was set free, racing across the cosmos for all time. We see that light today as the cosmic microwave background, a faint, cold glow that fills every direction of the sky. It is the oldest light we can observe, a baby picture of the entire universe. This ancient glow is not perfectly uniform. If you could see it with eyes sensitive to temperature, you would notice a mottled pattern, a tapestry of spots that are ever so slightly warmer or colder than their surroundings. These tiny fluctuations, mere millionths of a degree, are the most important features in the cosmos. Each warm spot marks a region that was slightly denser, a region where a little more matter was gathered. Each cool spot signifies a region that was slightly emptier. These are the primordial seeds, the original quantum ripples magnified to a cosmic scale. They are the blueprint for the entire cosmic web. Gravity saw this blueprint and got to work. Over billions of years, it pulled matter relentlessly toward those warm, dense spots, sculpting them into the great clusters and filaments. It evacuated the cool, underdense regions, creating the vast cosmic voids. The map of the universe we see today is a direct, blown-up tracing of this ancient pattern. We can test this connection mathematically. By studying the statistical properties of the CMB's modeling, cosmologists can predict the statistical distribution of galaxies. The patterns match with stunning precision. Space missions like Planck have mapped this fossil light with such exquisite detail that we can read it like a historical document. The sizes and distribution of the hot and cold spots strongly confirm our core model of cosmic evolution, the lambda cold dark matter model. They tell us how much dark matter and dark energy must exist, and how fast the primordial ripples had to grow to build the universe we inhabit. This cold, microwave glow is more than a relic. It is a prenatal ultrasound for the cosmos. It shows us the invisible scaffolding at the very moment of its birth, a ghostly framework that would one day be clothed in galaxies, stars, and life. Einstein's theory of general relativity gives us a way to see the invisible. It predicts that mass warps the fabric of space-time, and light, traveling through that warped space, must bend its path. This is gravitational lensing, and it is one of our most powerful tools for mapping the cosmic web's dark skeleton. Imagine you are looking at a distant cityscape through the rippled glass of an old window. The buildings appear stretched and distorted, their shapes subtly aligned by the imperfections in the glass. Astronomers do something very similar on a cosmic scale. They look at millions of faint, distant galaxies, and they search for tiny, systematic distortions in their shapes. These are not the dramatic arcs and rings of strong lensing, but a far more subtle signal known as weak gravitational lensing. Each individual galaxy's distortion is minuscule, almost imperceptible. But when you analyze the shapes of millions of them, a pattern emerges. Their slight, coherent stretches point toward the unseen sources of gravity that lie between them and us. This vast statistical analysis allows scientists to create a mass map of the cosmos. They are not mapping light, they are mapping gravity itself. The resulting charts reveal the ghostly contours of dark matter filaments stretching between galaxy clusters, vast rivers of invisible mass that the distorted starlight has traced for us. This technique has directly confirmed a key prediction of the cosmic web model. We have now seen, through this indirect but powerful vision, how dark matter forms bridges between colossal clusters, exactly as the simulations foretold. It turns the entire universe into a natural observatory, using the light from distant galaxies as our probe and the warping of space-time as our measure. By weighing this cosmic scaffolding, we are not just confirming its existence, we are learning about its density, its structure, and the sheer amount of mass required to hold the entire universe together. What other invisible forces might be bending the light from the farthest reaches of space, waiting to be decoded? This diffuse atmosphere is the universe's ultimate recycling system. The intergalactic medium is the tenuous gas that fills the vast expanses between galaxies, a ghostly haze of mostly hydrogen and helium so thin it makes the best laboratory vacuum on Earth seem dense by comparison. This is not a uniform fog, but a substance sculpted by the cosmic web itself, the gas pools within the great dark matter filaments, flowing along these invisible riverbeds while the voids are left as near empty deserts. Where this river of gas is channeled into the gravitational wells of galaxies, it provides the essential fuel for star birth, a continuous accretion that breathes new life into aging galactic cities. To study this phantom atmosphere, astronomers decode the shadows it casts. As the brilliant light of a quasar journeys across the cosmos, it passes through these filaments. Atoms within the intergalactic medium absorb very specific colors from this light, leaving a unique pattern of dark lines in the quasar's spectrum. This cosmic barcode is incredibly revealing. It allows scientists to measure the temperature, density, and even the chemical composition of the gas from billions of light years away. The most profound discovery from this shadow play is that this primordial gas is not perfectly pure. It contains trace amounts of heavier elements, carbon, oxygen, and silicon, the very elements forged in the hearts of stars and scattered by titanic supernova explosions. This means the intergalactic medium carries the fossil record of cosmic history. It has been enriched over billions of years, polluted by the ashes of the very first generations of stars and galaxies. Every atom of oxygen we breathe was once part of this vast circulating system, ejected from a long-dead star to travel the cosmic web before finding its way into our solar system. The story of life is written in the faint, elemental whispers of this universal atmosphere. Your galactic address within this cosmic network is more than just a location, it is a destiny. A galaxy's position on the web determines whether it will be a vibrant stellar nursery or a quiet retirement home for ancient stars. This environmental dependency is one of the most powerful forces in galactic evolution. Picture the dense urban core of a galaxy cluster. This is a gravitational metropolis, but for the galaxies living here, it is a dangerous and taxing environment. They whip past each other at incredible speeds, and in this frenetic dance, a galaxy can be brutally stripped of its lifeblood. A process known as ram pressure stripping occurs as a galaxy rams into the superheated intracluster gas that fills these spaces. This acts like a cosmic wind, blowing away the galaxy's vast reservoirs of cold hydrogen gas, the very raw material needed to create new stars. Without this fuel, star formation grinds to a halt. The galaxy's population of massive, hot, blue stars quickly burn out, leaving behind only the longer-lived, cooler, red stars. This is how a spiral galaxy, once rich with gas and dust, can be transformed into a red and dead elliptical galaxy, a celestial ghost town whose star-forming days are over. The cluster environment, for all its brilliant crowds, is a place of galactic senescence and quietus. Now, journey out from these crowded hubs and into the great filaments themselves. These are the cosmic countryside, the vibrant interstates feeding the urban centers. Here, galaxies are not isolated, but they are spaced far enough apart to avoid constant violent encounters. The key here is the steady, gentle inflow. The dark matter filaments act as gravitational conduits, channeling a continuous supply of fresh, cold gas from the cosmic web directly toward these galaxies. This constant nourishment allows them to maintain healthy, ongoing star formation. They are often gas-rich spirals like our own Milky Way, their pinwheel arms glowing with the blue light of newborn stars. Their position on the cosmic highway provides a reliable delivery of resources, keeping them active and alive for billions of years. Finally, consider the most remote locations, the deep cosmic voids. Here, a lonely galaxy might drift in profound isolation, an island in an ocean of near-nothingness, shielded from the gravitational harassment of neighbors and the stripping winds of cluster gas. These isolated galaxies should, in theory, be perfectly preserved. They might hold onto their primordial gas for eons, evolving at a glacial pace. Yet, this very isolation might also be a curse. Without the occasional gentle merger or the influx of new gas from cosmic filaments, their star formation may simply putter out from a lack of fresh stimulation. They could become quiet, anemic galaxies, not from violence but from solitude. This is the cosmic ecosystem in action. A galaxy does not control its own fate. It is a product of its environment. Its access to resources, its exposure to cosmic weather, and the density of its neighborhood, all dictated by its place in the web, will ultimately decide whether it becomes a brilliant beacon of new life or a fading ember in the dark. The James Webb Space Telescope is now witnessing the cosmic web's birth. Its unparalleled infrared vision pierces through time, looking back more than 13 billion years to an era when the universe was a construction site. Astronomers are hunting for protofilaments, the faint, gaseous precursors to the great cosmic highways we see today. These are not the bright, galaxy-studded rivers of the modern universe, but the ghostly blueprints themselves, the first threads of dark matter and primeval hydrogen gas that began weaving the cosmos together. The stunning revelation is that this framework was established with breathtaking speed. Even before the first galaxies had fully taken shape, these filaments were already stretching across the primordial darkness, connecting pockets of early star formation. We are no longer just predicting this infant web through simulations. We are starting to see its direct observational signature. JWST deep field images reveal incredibly distant galaxies, and between them a faint diffuse glow. This is the light from hydrogen gas that has been heated by the first stellar radiation, tracing the very strands of the nascent web. It confirms that the invisible dark matter skeleton dictated the flow of matter from the very beginning, guiding the first clumps of gas into the gravitational wells where galaxies would be born. This period, known as the Epoch of reionization, was a cosmic dawn when the first stars and black holes switched on and began flooding the universe with light. That intense radiation blasted apart the neutral hydrogen atoms that filled space, burning cosmic bubbles of clarity into the primordial fog. The protofilaments were the conduits through which this transformative energy traveled, the channels that helped reionize the entire cosmos. By studying these infant structures, scientists have a direct test for our models of dark matter. Does the gas flow along the predicted paths? Do the filaments have the right thickness and density? The early answers from JWST data are a resounding yes, providing a powerful confirmation that our basic understanding of cosmic structure formation is correct. We are watching the universe's largest structure take its very first breath. The serene appearance of these cosmic rivers is a grand illusion. Within their vast volumes, a hidden tempest rages. As galaxy clusters collide and merge, they send titanic shock waves reverberating through the connecting filaments, like a sonic boom propagating through a celestial canyon. These collisions heat the diffuse gas to staggering temperatures of millions of degrees, stirring it into a state of immense turbulence. This is not a gentle flow, but a chaotic, churning sea of plasma, where energy cascades from colossal scales down to the smallest eddies. This turbulence is a crucial piece of the cosmic puzzle, as it governs how efficiently the gas can cool and condense to eventually form new stars, effectively setting the rate of galactic growth. Woven through this turbulent plasma are magnetic fields, invisible threads of force whose origins are a profound mystery. Were these fields generated in the early universe and stretched to cosmic scales by inflation, or were they seeded by the first stars and galaxies and then blown out into the web by galactic winds? Their presence is pivotal. Magnetic fields can channel the flow of gas, suppress turbulence, and prevent particles from diffusing away, acting as an invisible skeleton within the already invisible skeleton of dark matter. They add a layer of stunning complexity to the web's anatomy. Adding to the enigma, these filaments are likely highways for the universe's most elusive travelers, ultra-high-energy cosmic rays. These are not mere particles, they are subatomic bullets carrying energies millions of times greater than anything produced in our most powerful particle colliders. Their exact sources are unknown, but they are thought to be accelerated in the most violent environments imaginable, like the jets of supermassive black holes or the shock fronts of galaxy cluster mergers. Once unleashed, these particles would be funneled and confined by the filament's magnetic fields, traveling along these cosmic conduits for millions of light years. Detecting them is incredibly difficult as their paths are bent by magnetic fields, obscuring their origin. Finding a way to trace these particles back to their source would be like discovering a map to the universe's most powerful particle accelerators. Unraveling the intricate dance of turbulence, magnetism, and these extreme particles requires a fusion of scientific disciplines, from the large-scale laws of cosmology down to the microscopic rules of plasma physics. It is a monumental challenge that pushes the very limits of our knowledge. What other invisible forces are at work within the deepest veins of the cosmos, shaping its evolution in ways we are only beginning to perceive? This grand cosmic architecture forces us to confront a fundamental question about the universe's very nature. Is the cosmos fundamentally the same everywhere, or is it a unique and uneven tapestry? For centuries, science has operated on a profound assumption called the cosmological principle. It states that on the largest scales, the universe is both homogeneous and isotropic. Homogeneous means the overall mix of matter and energy is evenly distributed, like a well-mixed batter. Isotropic means it looks the same in every direction you look, with no special center or edge. This principle is the bedrock of modern cosmology. The reason we can assume the laws of physics we discover here apply in the most distant galaxy. Yet the cosmic web, with its colossal walls and cavernous voids, appears to be a direct challenge. When you map the universe on a scale of a few 100 million light-years, it looks anything but uniform. It is a landscape of dramatic peaks and abyssal valleys, a cosmic geography that seems wildly uneven. So, does this mean the cosmological principle is wrong? The answer lies in the scale of the averaging. Imagine you are flying over a mountain range. From a low altitude, you see only the jagged peaks and deep ravines, a terrain that is clearly not smooth or uniform. But if you ascend to the edge of space and look down, those same mountains blur into a mere texture on the planet's crust. The continents and oceans become the dominant features, and the Earth appears as a smooth sphere. Cosmologists argue this is exactly what happens with the universe. When you zoom out to scales of 1 billion light-years or more, and you count all the matter within those immense volumes, the dramatic hills and valleys of the cosmic web do indeed average out to a remarkably smooth distribution. The voids balance the clusters, and the filaments connect it all into a statistically uniform foam. This delicate balance, however, is being tested by the discovery of truly monstrous structures. One contender is the Hercules Corona Borealis Great Wall, a possible conglomeration of galaxies stretching an almost inconceivable 10 billion light-years across. If confirmed, its sheer size would represent a significant deviation from the smoothness predicted by the cosmological principle on its intended scales. Is this wall a fatal crack in our foundational assumption, proof that the universe possesses structures of such grandeur that they defy uniformity? Or is it merely a rare statistical fluke, the universe's largest possible lottery win, a chance clustering in an otherwise homogeneous cosmos? This is not an abstract debate. The answer dictates how we interpret everything from the cosmic microwave background to the universe's ultimate fate. It forces us to ask whether our vantage point is truly typical, or if we are, by some cosmic coincidence, residing in a region that is unrepresentative of the whole. The cosmic web has not just mapped the universe, it has placed our most fundamental assumptions under a microscope, challenging us to see if the cosmos is truly uniform, or if its greatest marvels are its most profound exceptions. The cosmic web is a judge, delivering verdicts on our boldest ideas about the universe. While the standard model of cosmology has been remarkably successful at predicting its immense architecture, this very structure is also the ultimate proving ground for theories that dare to challenge the mainstream. One of the most persistent alternatives questions the very existence of dark matter. Modified Newtonian dynamics, or MUND, proposes that our understanding of gravity is incomplete. It suggests that on the scale of galaxies, gravity behaves differently, becoming stronger at very low accelerations, which would explain why stars at the outer edges of galaxies orbit just as fast as those near the center, a phenomenon usually attributed to the gravitational pull of unseen dark matter. For a single galaxy, this idea can seem elegant, but the cosmic web presents a monumental problem. MUND, in its original form, struggles to explain the violent dynamics within colliding galaxy clusters, where the observed gravitational effects are clearly separated from the visible matter. It has immense difficulty reproducing the specific, mottled pattern of the cosmic microwave background, the universe's baby picture, which strongly requires the presence of dark matter to look the way it does. The intricate filamentary structure of the web itself, with its specific distribution of voids and clusters, is a fingerprint that MUND has found nearly impossible to replicate without invoking some form of hidden matter, undermining its core premise. Beyond MUND, other fascinating ideas emerge. Could the universe have a fractal nature, repeating similar patterns of clustering across every scale, from the smallest to the largest? Detailed maps of the cosmic web show that this is not the case. The clustering smooths out and changes character at the largest scales, defying a simple fractal law. Or what about the influence of powerful, primordial magnetic fields, woven into the fabric of space from the beginning? While magnetic fields do exist within the web's filaments, their observed strength is too weak to have been the primary architect of such colossal structure. Each of these alternative visions is a testament to human ingenuity, a desire to see the cosmos through a different lens. Yet when confronted with the cold, hard data of the cosmic web, their shortcomings become apparent. This relentless testing is how science progresses. The web's precise geometry and the exact motions of galaxies within it act as a cosmic filter, sifting through possibilities. Theories that cannot account for the full splendor of this interconnected network are refined or must be set aside. This process does not stifle innovation, it guides it. It tells us that if new physics is to be found, it must be physics that can build a universe looking exactly like our own, a universe connected by a web of dark and light. What deeper layers of reality must we uncover to fully comprehend the judge's final ruling? Every person and planet we have ever known resides within a single, unremarkable filament of the Laniakea supercluster. Our Milky Way galaxy is not a central metropolis but a quiet town along a vast cosmic highway, one thread in an unimaginably large tapestry. This realization delivers a profound dual meaning. We are, by any physical measure, infinitesimal, a biological whisper in a universe of gravitational shouts. Yet this very smallness is woven into the grandest structure known to exist. The iron in your blood and the calcium in your bones were not born here. They were fused in the heart of a long-dead star that lived and died long before our sun was even a cloud of dust. When that star ended its life in a cataclysmic supernova explosion, it blasted those newly forged elements out into the galactic winds. Those atoms then began an epic journey, swept along the currents of the cosmic web. For billions of years, they circulated through the warm, hot intergalactic medium, traveling the invisible filaments until gravity finally gathered them into the molecular cloud that would become our solar system. You are not just living in the universe, you are a literal piece of it, a temporary assemblage of ancient stardust that has traversed the largest of scales. And the most staggering part of this story is not just that we are part of this web, but that we can understand it. With nothing but curiosity, mathematics, and the faint light reaching our telescopes, we have mapped the invisible continents of dark matter and traced the ghostly rivers of intergalactic gas. This intellectual achievement connects our tiny world to the cosmos in a way that is both humbling and deeply empowering. Our quest to comprehend the cosmic web is the universe, in a very real sense, beginning to understand itself. Our current map of the cosmic web is about to be rendered a crude sketch. The next decade will see a revolution in our vision, driven by a new generation of observatories with capabilities that dwarf our current tools. The Vera C. Rubin Observatory, perched high in the Chilean mountains, will embark on an unprecedented 10-year mission called the Legacy Survey of Space and Time. Its massive mirror will scan the entire southern sky, not once, but over and over, capturing the images and distances of billions of galaxies. This will not be a static snapshot. It will be a time-lapse movie of the cosmos, revealing how the web's filaments subtly shift and stretch over eons, providing a dynamic view of its evolution. In space, the Nancy Grace Roman Space Telescope will act as a powerful complement. With a field of view 100 times larger than the Hubble Space Telescopes, it will perform vast, high-resolution surveys designed to measure the precise shapes of billions of galaxies. This will allow astronomers to perform weak gravitational lensing on an industrial scale, creating exquisitely detailed mass maps of the dark matter filaments and quantifying how dark energy is actively straining the web's architecture. The most profound shift, however, may come from listening rather than looking. The Square Kilometre Array, a network of thousands of radio antennas spread across 2 continents, will tune into the universe's primordial hum. It is designed to detect the faint radio signature of neutral hydrogen gas, the primary component of the cosmic web's filaments. This telescope could trace the web's gaseous skeleton directly, bypassing the galaxies entirely to map the raw, flowing rivers of matter themselves. It would be like seeing the hidden watershed of a continent for the very first time, in perfect detail. Together, these instruments will transform the cosmic web from a grand silhouette into a living, breathing entity whose history, composition, and ultimate fate we can finally begin to read. What long-hidden chapters of cosmic history will these new eyes reveal when they turn toward the dark? The universe's grandest structure compels us to ask if existence is ruled by chance or by a deep, underlying order. From the seething, chaotic froth of quantum fluctuations in the first moment, a pattern of breathtaking regularity emerged, a cosmic lattice connecting every galaxy. This transition from primordial chaos to intricate structure is not random. It is the direct outcome of a simple set of physical laws playing out over billions of years. Gravity's relentless pull and the expansion of space itself acted as cosmic sculptors, transforming microscopic randomness into macroscopic majesty. The web is a testament to the power of simple rules to generate boundless complexity, a dynamic that echoes in nature from a snowflake's formation to the branching of a tree. This cosmic architecture challenges our deepest intuitions. Does such magnificent organization imply a guiding hand, a grand design, or is it simply the inevitable, beautiful consequence of physics unfolding? The web offers no easy answer, but it powerfully suggests that our universe is fundamentally creative, capable of weaving immense complexity from the humblest of beginnings. This physical interconnectedness has resonated far beyond science, inspiring both spiritual reflection and a profound sense of unity. The same filaments that channel galaxies also delivered the atoms that built our world. We are not merely observers of this web. We are a conscious expression of its interconnected nature, a fleeting moment in which the cosmos can contemplate its own stunning and coherent whole. Despite our remarkable maps of this cosmic continent, its deepest mysteries only grow more compelling. We have traced the invisible skeleton, but we still do not know what dark matter actually is. Is it a sea of exotic, undiscovered particles, or does it point to a fundamental misunderstanding of gravity itself? This question remains the single greatest puzzle in all of physics. Within the filaments, another enigma churns. How are the magnetic fields that thread through this tenuous gas actually born? Were they stretched to cosmic scales in the universe's first instant, or are they the accumulated breath of countless stellar winds and supernova blown out into the intergalactic void? Their origin story is still being written. We also lack a complete picture of the cosmic life cycle of ordinary matter. We see gas flowing from the voids into the filaments and down into the galaxies, but the precise details of this accretion are murky. How does this diffuse, superheated gas actually cool and condense to fuel star formation? What are the exact roles of violent galactic feedback, where supernova and black holes blast material back out into the web, regulating the growth of galaxies? This intricate dance of inflow and outflow is the heartbeat of galactic evolution, and we are only beginning to learn its rhythm. And on the grandest scales, a haunting question persists. Are the colossal structures we have mapped, like the Sloan Great Wall, truly the largest things in existence? Or do our surveys merely hint at even more immense patterns lying just beyond the limits of our current vision? Each new discovery does not close a book, it opens a doorway. The cosmic web is a living frontier, a constant reminder that our understanding of the universe is perpetually unfinished, always inviting us to look deeper into the dark. The same mathematical elegance that governs a snowflake's growth also sculpts the cosmic web. When supercomputers translate the universe's raw data into visual form, they reveal an architecture of breathtaking beauty, a tapestry of light and shadow that rivals the most profound works of abstract art. These are not mere diagrams, they are digital visions of reality, showing luminous filaments flowing into brilliant nodes, a structure that feels both alien and strangely familiar. It echoes the branching of a tree's roots, the intricate firing of a human brain's neural network, and the delicate tracery of a leaf's veins. This recurring pattern across scales, from the microscopic to the cosmic, is not a coincidence. It points to a deep, universal logic of network formation, where efficiency and resilience emerge from simple rules of connection and flow. This stunning convergence of form has sparked a powerful collaboration between scientists and artists. Data visualizers and digital artists take the trillions of data points from cosmological simulations and translate them into immersive experiences. They assign color and texture to dark matter, give volume to the invisible rivers of gas, and allow us to fly through the vast voids. These creations are more than just pretty pictures, they are bridges of understanding. They transform abstract equations and spectral lines into something our senses can grasp, making the invisible architecture of our universe tangible and emotionally resonant. By engaging with the cosmos as both a physical system and a work of art, we access a more complete form of knowledge. We move beyond simply knowing how the web forms to feeling our place within it. This fusion of empirical truth and aesthetic wonder does not diminish the science, it enriches our relationship with the universe. It reminds us that our quest to map the darkness is also a search for meaning and connection, a way to appreciate the profound beauty woven into the fabric of everything. Our own cosmic web might be just one pattern in an infinite tapestry of realities. This idea pushes into the most speculative frontiers of physics, where the concept of a multiverse emerges. Some theories propose that our entire universe is but one bubble in a vast, frothing cosmic foam, where countless other universes are continuously budding into existence, each with its own unique set of physical laws. In this breathtaking scenario, the specific quantum ripples that seeded our web of galaxies could be entirely unique to our cosmic bubble. Another universe might have experienced a different kind of inflation, resulting in no large-scale structure at all, a silent, eternal expanse of uniform darkness. Or perhaps its web is far denser, a frenzied knot of galaxies, or so sparse that matter never coalesced into a single star. The very parameters that allowed our universe to build this intricate architecture, and in turn to forge the elements for stars, planets, and life, might be an exceptionally rare combination in a wider, mostly barren cosmic landscape. While this remains a profound hypothesis, untestable with our current science, it uses the reality of our cosmic web as a tangible starting point for the ultimate question. Is our beautifully structured universe a cosmic necessity, or is it a single, fortunate island of order in a multiverse of endless, silent chaos? Our journey through the cosmic web reveals a universe of breathtaking connection. This is not a random scattering of stars, but a single, coherent structure of unimaginable scale. An architecture where the invisible threads of dark matter dictate the destiny of every galaxy. We have traced this network from its birth in quantum whispers to its present form, a tapestry woven with glowing filaments and vast, silent voids. It governs the brilliant birth of stars in spiral galaxies and the quiet senescence of red giants in dense clusters, a cycle of cosmic life and death choreographed by gravity. The questions it raises are as profound as the structure itself, challenging our most fundamental assumptions about the cosmos. This grand web stands as a monumental testament to human curiosity, a victory of reason that allows us to map a continent we cannot see. As our next generation of telescopes peels back deeper layers of this mystery, we must remember our unique place within it. We are not passive witnesses to this cosmic story. We are active participants, living on a planet built from atoms that once traveled these very filaments. Our quest to understand the web is the universe awakening to its own existence. If this exploration of the cosmos's deepest connections has captivated you, subscribe for more journeys into the heart of space's greatest mysteries. We would love to hear your thoughts on this incredible structure